So in this set of problems, we're going to look at various nuclear decay types. So let's start off with alpha decay. So the alpha decay equation, we have a starting nucleus with Z protons and A nucleons, and it gives off a helium nucleus with 4 nucleons and 2 protons. So it's going to be 2 protons, 2 neutrons, and that's called an alpha particle. And then it gives off another large nucleus which has 2 less protons and 2 less neutrons. So the top number goes down by 4 and the bottom number, the Z number, goes down by 2. So let's do some examples. So I've got 21084 polonium. And so what's going to happen is it's going to give off a helium nucleus, so 42 helium, plus, now I'm going to calculate 210 minus 6, so minus 4 is 206, 84 minus 2 is 82, and so I need to choose my X prime, that's code for the symbol that has a Z of 82, so I go over to my periodic table, and I look, where's 82? 82 is over here. It's lead, so Pb is the symbol. Okay, so it goes to lead plus an alpha particle. Or how about uranium-238? Well, it gives off an alpha particle, 42 helium, plus it gives off a nucleus that has 4 fewer nucleons, so 238 minus 4, which is 234, and 2 fewer protons, so 92 minus 2 is 90, and then I go to the periodic table, look at what is 90, so where's 90? 90 is down in this extra bit at the bottom, it's thorium, Th. Alright, so I'm going to put in the symbol Th. Alright, next one I'm starting with now, thorium-238. So what does it give off? Helium alpha particle. And the top number goes down by 4, so 238 goes to 234. The bottom number, 90, goes down by 2 to 88. And again, go to my periodic table. What's 88? 88 is over here on the left. Radium, Ra. And depending, you might see this written as just alpha plus 234, 88 radium. Alpha and 42 helium is the same thing. All right, let's do beta minus decay. So for beta minus decay, we have a nucleus. It gives off an electron, which is sometimes also called a beta minus particle. It gives off an electron, and so it adds a negative charge on the right side. So to compensate for that, to make it, we've got a charge of plus Z on the left side, and I'm subtracting a charge on this side, so I need to have Z plus 1 positive charges on the other side. So I need to step one place up in the periodic table to an atom that has Z plus 1 protons in it, so that I get the same net charge on each side. So the charge has to be conserved. The nucleon number has to be conserved. So in the electron, sometimes that's written as a 0 at the top and minus 1. You might see it written as 0 minus 1e. And so what that means is that if I want to add up the numbers on the top and the bottom, you can see I would have Z is equal to Z plus 1 minus 1, or A is equal to A plus 0. Okay, so I'm going to keep my A number the same, but I'm going to jump up one spot in the periodic table. All right, so I'm going to start off with 14,6 carbon, and I'm going to leave the 14 the same, top number stays the same, but I'm going to jump one up in the periodic table, and hopefully we know the periodic table well enough, but let's just go up and take a look. So carbon, I'm over here, I'm going to jump up one spot, which will take me to nitrogen. All right, so it's going to be 14,7 nitrogen. So I increase the bottom number, the Z, by 1. And it gives off an electron plus It also gives off what we call an antineutrino, and that's there to conserve energy and momentum. All right, how about strontium? So I've got 90, 38 strontium, so my 90 stays the same. The bottom number goes up by 1, so I go to 39. I jump up 1 in the periodic table, so go back to my periodic table. So I'm going to jump to 39. 39, I go from strontium up to yttrium. So I'm going to go to Y. And again, it gives off an electron and an antineutrino. Okay, how about potassium? So I've got potassium, 40. What does that go to? The 40 stays the same. The 19 goes up to 20. So again, hop to my periodic table. All right, so I've got potassium, that's over on the far left side. Potassium goes up to, from 19 to 20, I get calcium. All right, so I got calcium, and again, plus an electron and a neutrino. Okay, so that was beta minus decay. Beta plus decay, now I give off a positron. Okay, so positron is an electron with a positive charge instead of a negative charge. So that's sometimes written as E with a plus 1, 0. So you can see that if I look at, let me write this down here, look at the bottom number, Z minus 1 plus 1 equals Z, and A plus 0 equals A. So you can see the nucleon number is conserved and the charge is conserved. And also a neutrino is given off, and again, that's to conserve energy and momentum. Okay, so let's do these examples. So I've got 116, 50, tin. So what's going to happen? I've got 116 is going to stay the same. The 50, now I jump down 1 spot in the periodic table, so my 50 goes to 49. Okay, so I look at what's 49 in the periodic table. 49 is indium, In, and of course it gives off a positron plus a neutrino. All right, 61, 29 copper. So I go 61, jump down 1 spot in the periodic table, so I'm going to go to 28. And 28 in the periodic table is right in the middle there, that's nickel. Plus a positron plus a neutrino. Okay, and let's see, I've got 30, 16. So I'm going to, 30 stays the same. 16, I'm going to drop down 1 in the periodic table down to 15. And 15, I go from sulfur down to phosphorus. So I've got a P, and of course, a positron plus a neutrino. Okay, so if you're given what kind of reaction it is, then it's pretty straightforward just to use the correct equation, reaction equation, to give the right answer. What if you're given a partial reaction? So I'm going to zoom in on this a little bit because it might be a bit small. Okay, so I've got to fill in, complete this reaction. All right, so you can see here, I've got, in this first equation, this is written in this way, like I was talking about earlier. So this, I guess it didn't want to stay zoomed, that's an electron. Okay, so it gives off an electron, so I know that must be a beta minus decay. All right, so what I need to have is the top numbers and the bottom numbers have to add up to be the same on both sides. So on the right side, I've got 14 plus 0, so it's going to give me 14. On the right side, I've got 14 minus 1, so that gives me 6. And so all I have to do is go look in the periodic table. What's the 6th element in the periodic table? And it's carbon. All right, so that finishes that equation. That was a beta minus decay. Okay, next one, I've got 23892 uranium going to 23490 thorium. I think we actually had this up in an earlier problem. So now I compare my numbers. So again, I have to have the total number at the top be the same. So I've got 238 on the left. So I must have a 4 over here, so that 234 plus 4 will equal 238. And the bottom, I have to have a 2, so that 90 plus 2 equals 92. And what's that? That's a helium nucleus. So this is just an alpha particle. So that's alpha decay. All right, bottom one. Now I've got 15 and 15. So I must have 0 left on this side. 8 and 7, so I must have a plus 1 at the bottom. So 15 plus 0 is 15, 7 plus 1 is 8. And what is that? That is my positron, like I was talking about. So this is a beta plus decay. You'll notice that in these equations, they didn't put in the antineutrino and the neutrino. So sometimes you'll see nuclear reactions written online without the neutrinos in for the beta minus and beta plus. That's strictly not correct, but you will often see them written as a balanced equation without those neutrinos in them.